Hello, everyone. Welcome to the Math Magician's Den. This is the Herm Dog, and today we're going to talk about derivatives again. But what about functions, exponential functions that have a base that's not e? In fact, these formulas could work if the base was e as well. The derivative with respect to x of e to the x, if you watch one of my previous videos, we know that's e to the x. Well, this formula says it should be e to the x times the natural log of e. But the natural log of e is just 1, so it comes out to be e to the x, which does work. It's the same thing with the derivative with respect to x of e raised to a function u. The derivative would be u prime times e to the u, and this formula says you should multiply by the natural log of e, but again, the natural log of e is 1. So this comes out to be u prime e to the u. So these formulas do work for e. But we never write the natural log because there's no point. It's the natural log of e is just 1. So what is the derivative of 2 to the x? The derivative of 2 to the x would be 2 to the x times the natural log of the base, the natural log of 2. So this is how we do the derivatives of bases that are other than e. So what's the derivative of 3 to the x squared power? The derivative of 3 to the x squared power is 3 raised to the x squared times the natural log of 3. But what you have to do, chain rule says I have to multiply by the derivative of the exponent. So I'm going to multiply by 2x. There's my derivative. Now, what if I have 5 to the 3 divided by x? You would write 5 raised to the 3 divided by x. So just rewrite the exponential. You're going to multiply by the natural log of the base. And then what you're going to do out front is you're going to multiply by the derivative of the exponent, which would be negative 3 over x squared. Same thing here, derivative of 6 to the x, or 6 to the x would be 6 to the x natural log of 6. Well, this one we're going to write 6 raised to the cosine of x. We are going to multiply by the natural log of the base, which would be the natural log of 6. But then I have to multiply by the derivative of cosine, which is negative sine of x. So I would get negative sine of x times 6 to the cosine of x times the natural log of 6. Seems pretty simple so far. It is exactly like taking the derivative of e to the x, except we're doing something not really different. We're just multiplying by the natural log of the base. Now, let's do a problem where it involves a product rule. How would you find f prime here? Well, the derivative of 2 to the x would be 2 to the x natural log of 2, and we have to multiply that by x to the 4th. Product rule is plus. Then I would have to take the derivative of x to the 4th, which would be 4x cubed times 2 to the x. And I'm not multiplying by the natural log of 2 here because I didn't take the derivative of the exponential. The next problem as you move down the page here, this one involves a product or a quotient rule. And when we do a quotient rule, we have to take the derivative of the top first, which would be 7 raised to the 2x times the natural log of 2. Sorry, I apologize. We'd have to multiply by the natural log of 7 because the base is 7 here. But then I have to multiply by 2 out front. And that has to be multiplied by the bottom. Quotient rule is minus. We're going to take the top, which is 7 to the 2x, and I'm going to multiply that by the derivative of the bottom, which is 4x cubed, all over the bottom squared, which would be x to the 8th. Now, we could do some simplifying here. I could cancel out an x cubed from all of these, and I would get 2 times 7 to the 2x natural log of 7 times another x, and I'm going to put that x up front here, minus 4 times 7 to the 2x all over x to the fifth. And that would be my final answer. Now, some people will ask me, and I know they've done this in class before, well, why can't I multiply these and make it 28? You can't. You'd have to do the exponent first. And in the exponent, I can't really simplify 2 to the x. Now, one thing I could do right here to make my life easier, in fact, I could have done it at the beginning of the problem. I could have said this was 7 squared, 49 to the x, divided by x to the fourth. And this might have made my problem a little easier in terms of, hey, I don't have to worry about doing a chain rule on the 49 to the x. So that is an option I could have had. Let's do a chain rule problem here. What is the derivative of cosecant? Well, it's negative cosecant squared of 6 to the x squared. What's the derivative of 6 to the x squared? Well, it's 6 to the x squared multiplied by the natural log of the base, which is 6, times the derivative of the exponent, which is 2x. Wow, that's a lot. In fact, I'm not going to worry about simplifying on that one. The only thing we could really do is bring the 2x out front. And let's do a problem here with the higher order derivative. What's y prime? Y prime would be 5x to the fourth plus, it would be 2 to the x to the fifth, natural log of 2, and I would have to multiply by 5x to the fourth. That's my first derivative. My second derivative, again, I'd have to do a power rule. It would be 20x to the third, and this here I'd have to do a product rule. So this would be 20x to the third times the second part, which is 2 to the x to the fifth, natural log of 2. Product rule is plus, we'd put 5x to the fourth. I'd have to multiply by 2 to the x to the fifth, and I'd have to multiply by another natural log of 2. Not to mention, I'd have to multiply by another 5x to the fourth, the derivative of the exponent. This is ugly. So I get 20x cubed plus 20x cubed times 2 to the x to the fifth, natural log of 2. And then for the last term here, I'm going to get 25x to the eighth times 2 to the x to the fifth, and then the natural log squared of 2. So you can see how we do derivatives of exponentials that involve a base that's other than e. And again, these would all work. This would all work the same way if I put e as the base of all of those exponentials. Hope you enjoyed the video. If you like my videos, please like and subscribe. I will see you soon.